over part 2 for DielsAlder, and we're diving into the regioselectivity and the stereoselectivity of this reaction. So here I have 2 examples of 2 different dienophiles. Notice that one is a cis and one is a trans. And just for review, let's just label our diene and our dienophile for the DielsAlder reaction. So we have our diene has 2 alkenes, and our dienophile has 1 alkene. And as you can see, our dienophiles always have at least 1 electron withdrawing group. Otherwise, this reaction is super slow. The thing about DielsAlder is it's a concerted reaction, so it all happens at the same time. Remember that our arrows here, essentially pushing into space, making a new bond between these 2 carbons. The alkene from the dienophile then pushes over to make a new bond, which forces this carbon here to lose a bond, and the double bond moves over. So let's draw what we have from here. We make our cyclohexene structure. There are 6 carbons in this ring. And notice that the nitrile and the methyl group here are on the same side of our alkene. It's a cis alkene. That means that when we draw our product, these 2 groups will in fact be on the same side. This product is racemic. We have 2 chiral centers and they can both be facing down, right? Let's do the bottom reaction here. Again, DielsAlder is done under heat. In this case, we have a trans dienophile, and this alkene shows that the nitrile and the methyl are on opposite sides of that double bond. Our arrows for this reaction are absolutely the same. But as you can see, our 2 groups here are switched. It's in a trans alkene form. So that means that one of them will be up and one of them will be down. We made 2 chiral centers here, just like in our top example. And these 2 chiral centers can both be switched. So that means we can write racemic, meaning that we get both of our 2 products, one where it's drawn like this and one where both of the stereocenters are flipped. So again, this is showing DielsAlder is a concerted reaction, and if you start with a trans alkene, like in our bottom example, you'll have both of those groups opposite of each other. If you start with a cis alkene, like in our top example, both of the groups are on the same side. Let's now talk about this rule with DielsAlder, and I'm giving you this rule so that it makes it a little easier for us to figure out the regioselectivity of this reaction, called the beside and opposite rule, okay? Essentially what I'm saying is that the electron donating group on the diene is either right beside or completely opposite of our electron withdrawing group on the dienophile. Let me show you what I mean by this. So here we have our diene and our dienophile. In our top reaction, you'll see that we have a diene here on the left and a dienophile on the right. On our diene, we have this methoxy group, and that is our electron donating group. On our dienophile, we have our ketone, which is our electron withdrawing group. These 2 groups should either be right beside each other or opposite. Let's draw what we have from here. We have our cyclohexene. I've counted the carbons with the orange color here. We have a methoxy group, and then our ketone is here. 1, 2, 3, 4 from our diene, and then 5, 6 from our dienophile. And on carbon 5, we have that ketone. For this arbitrary rule, we are considering these to be the 2 groups are beside each other, okay? And this is in fact favored. Let's look at the bottom example and let's see what happens if we flip our dienophile and see what kind of product we get. Here I've got my methoxy on the bottom carbon, and then the ketone here, it would have been on carbon 6. Let's count these carbons here. 1, 2, 3, 4, and then 5 and 6. That puts our ketone here if we draw the product based on how it's drawn here. This ketone is neither right beside or directly opposite. This would be disfavored because of that. So again, we want it either beside or opposite. Let me show you in a little more detail about what I mean by beside and opposite. So for this rule, we're making these cyclohexene structures. And if we have two groups here, I would consider this to be beside each other. They're right beside each other, right? If you run the reaction and you're able to draw the two groups with one carbon in between, this is not favored, okay? If you can draw the two groups opposite of each other, you've got your X and the Y group here, okay? This is what I'm calling opposite. So these are two favored regioselectivities for the Diels-Alder, okay? And so really what we're doing is just either flipping the dienophile to get the desired product here. So let's write this rule out again. So the most electron donating group on the diene, okay, and the most electron withdrawing group on the dienophile will be beside or opposite of each other. Let's do another example together. Here's a practice problem that we can go over. Notice that I'm using a very similar dienophile. And our diene here has an electron donating group. It's this methoxy. Our dienophile has our electron withdrawing group of the ketone. With heat, we're going to still make that cyclohexene ring. Now, let's figure out the placement of our groups. If I count this, 1, 2, 3, 4, and I'm going to put those same carbons here. This is from our diene. Our methoxy group is on carbon 3. Okay, so we have the methoxy group added. Now, what about the ketone? 5 and 6. The ketone is on carbon 6. The way that I have it shown here is that they are opposite. And from what we just talked about, this is in fact favored. Okay, this is a favored reaction, the favored product here for this DielsAlder. What would happen though if I took that dienophile and I flipped it? So we're going to draw the same diene, and let's just flip our dienophile. Okay, our methoxy is still on the same carbon, but our ketone is now on this carbon, right? This is disfavored. Okay, this is a disfavored formation of the product. So this is actually going to be our desired product here. Okay. What I want to do now is go over some of the electronics as to why this happens the way it does. You could also just remember this rule, and this will get you through. Let's look at let's do some resonance. Let's look at our diene and our dienophile, and we're going to do some resonance on these structures to see if this makes chemical sense. Let's take our diene. We know we have lone pairs on the methoxy, and we know that this is an electron donating group. We could draw a resonance form like this. okay, where that negative charge is on that N carbon. Let's do the same for our dienophile. We could draw this resonance structure, essentially an enolate resonance structure, right? This is essentially showing us that this structure of the diene has a partial negative charge on this N carbon. And the structure for our dienophile actually has a partial positive charge on this N structure. When these two react in this formation, this is how we end up getting our desired product where the groups are opposite of each other. So this is favored. Let's see what happens if we rotate our dienophile and making the disfavored formation, okay? So I'm going to take and redraw our diene with our partial negative. I'm going to flip the dienophile over. We know that our dienophile has the partial positive charge on this N carbon based on resonance. Notice here that this partial positive and our partial negative are not interacting in this scenario. This scenario is disfavored. And this is due to the electronics of these systems. In this case, in the bottom, we have the interaction of a partially negative carbon with this partially positive carbon. This is very favored. And so this is why we're going to be drawing either the product where the electron withdrawing group is opposite of our electron donating group, or if you can get it in a manner where they are beside each other, these are our two favored products. Now notice that the only reason why we can get the opposite one here is because of the placement of our original electron withdrawing group. Notice that it's one more carbon in compared to our previous example here, where we had the electron donating group on the very bottom carbon. And so this allows us to get that beside nature. You could go through the resonance for our first example and prove to yourself that this, in fact, also is chemically relevant with resonance. Okay, so now we've talked about regioselectivity, right? We have the beside and opposite rule to help us determine that. The next thing we need to do is look at these stereocenters. DielsAlder reactions create many stereocenters. And in this example, we would end up getting 4 stereocenters. Holy cow, that's a lot. So here we have 4 new chiral centers. Okay, this means that we have 2 to the 4, which would be 32 different stereoisomers. That's a lot of different products. Okay, there is a rule that will help us determine which one is favored, and it is called the Endoselectivity rule. So even though there's 32 possible stereoisomers, this Diels-Alder reaction generally makes 2 stereoisomers that are the major products. So these chiral centers are controlled by the endo-exo endoselectivity. Let's discuss the endo-exoselectivity. Here we've got cyclopentadiene and our dienophile is malic anhydride. Now, when we draw these reactions, we know that we have these p orbitals that are interacting. So here's our diene, okay? And I'm going to draw our dienophiles in blue here. Now, these reactions occur where the p orbitals will interact. The bottoms of one will interact with the tops of another. In this case, we have our electron withdrawing groups away from our diene, right? It is outside of that. It's approaching kind of like this, right? It is outside or exo compared to our diene. This will give us what we call our exo product. Let me draw this out. So we made a new carbon-carbon bond, and then what we did was we actually made a bicyclic ring here. Our two protons are now down, and our electron withdrawing groups are up. This is our exo product. It is thermodynamically favored. Let's see what happens when we have our electron withdrawing groups in the endo position here, which will be directly underneath our diene. So we're going to have our p orbitals. This is our diene, and then our dienophile is going to be directly underneath it. We still have the interactions of the two p orbitals here, okay? But notice that our ketones are directly underneath our diene, okay? They're directly underneath it. This is how we end up getting the endo product. So this is the endo product, and it is kinetically favored. For the reactions we're going to be doing, we're going to assume we are under kinetic control, okay? So this is the product that we're really going to be focusing on. So here I have our endo product, which is kinetically favored. And again, we're going to assume we're under kinetic control for these reactions. Our diene, though, it has these two protons, and I want to look at them in relation to the electron withdrawing groups on our dienophile. In our product, the two protons that I've pointed out on the diene are pointing down. Our electron withdrawing groups are also pointing down, okay? This endoselectivity, which is favored, shows that the outer groups on the diene they end up on the same side as the electron withdrawing groups on the dienophile. Okay. So let's draw this another way. It's going to be a little weird, but we're going to kind of look at this top down. You see this carbon that's pointing up? Let me circle it in red. We're going to look directly down onto that carbon, okay? So make it easier for us to see. So here's our CH2. This is what I have circled in red, okay? So we have our double bond. We've got our cyclohexene, okay? And then our endo product shows that these groups are pointed down. Okay. The protons that I showed you that were on the outer positions here, okay, must be pointing down. So this is kind of a skewed view of it, but you can kind of see from here that the electron withdrawing group and the outer groups on the diene are in fact on the same side, okay? Here I have it shown a little easier. Let's do this generic reaction to see what happens. So here I've got a diene and I'm labeling outer and inner. That's just meaning where they're placed at on the alkene, whether it's trans or cis. And then we have our electron withdrawing group. So let's draw the product using what we know about the endo-exo rule. We're going to make our cyclohexene structure, okay? So we'll put our outer positions back. And the inner groups will be coming forward, which means that our electron withdrawing group needs to be going the same way that our outer positions are going, okay? Same side there. This is our endo product, and this is favored, kinetically favored. Let's do a practice problem together using everything that we've learned about DielsAlder reactions. Here I have a diene, and I have it drawn in this straight chain form. And then we have our dienophile with this nitrile group on it. We know this is our electron withdrawing group, so that's good. And then we have this electron donating group, our methoxy. So this is very, very well set up to do a DielsAlder reaction. The first thing we need to do, though, is we need to rotate this single bond because we need this in the S-cis conformation. Right now, it's in the S-trans conformation, and this doesn't allow for any p orbital overlap. When we rotate this, I think it's so easy to flip this. And so what I like to do is label the alkene first. The alkene I have drawn here in green is a trans alkene. Notice the groups are opposite. So this is a trans alkene. And then let me label this other one in pink. And so here we have a cis alkene. Both of the groups are on the same side. So let's do our rotation here. Again, we have a trans alkene, and then here we have a cis, okay? So I'm going to first just draw a generic diene. I know that my top one here will be trans because we have a trans alkene. And then our bottom one here is a cis. So that means the deuterium is coming inward. Notice how the two groups are now. It's still a cis alkene. Okay, so we did our rotation into the S-cis. Let's redraw our dienophile. We are going to make a cyclohexene ring. Let's count our carbons. Okay. On carbon 1, we have a methoxy group. And then on carbon 4, we have our deuterium. Now, the way that I've placed this, we have our nitrile on carbon 6 right here. Let's count our carbons out. 4, 5, 6, okay? Does this satisfy the beside or opposite rule? Is our electron withdrawing group on our dienophile right beside the electron donating group on our diene? They are. So this is favored. You could draw another product where the nitrile is one more carbon away, and that would be disfavored, okay? So this is favored. Let me show you quickly how that would happen. So you'd use the same diene, and we would just flip, let's say this was drawn flipped over. This would cause you to draw a product like this. And this is not beside or opposite. Okay. All right. So now that we have our regioselectivity of where the groups are placed, now let's dive in, figure out what the stereochemistry of each of these new chiral centers is going to be. We know that this reaction is concerted. So our trans dienophile, where the nitrile and the ethyl group are opposite of each other, will hold true in the product. So this nitrile is opposite of our ethyl group. Now let's do our endo-exoselectivity to figure out the other two stereocenters here. We know that we have this diene, okay, and our methoxy and our deuterium are in different positions here. This methoxy would be considered to be in an outer position, right? And our deuterium is considered to be in the inner. This proton here is outer, okay, and inner. When I say inner, these are the ones that are kind of pointing towards each other in that diene. Remember that the outer positions should be on the same side as the electron withdrawing group. Our electron withdrawing group is the nitrile, and we arbitrarily put that it was coming forward. That means that the outer position, both of the outer positions should be coming forward. So the methoxy we're going to draw with a wedge. That means that our deuterium we're going to draw with a dash. Now we could have the stereoisomer where all of the chiral centers are switched. And so in this case, we're going to write racemic. And this is our favored product. So there you have it. You just did a complicated Diels-Alder reaction from the rules that we just went over. And that's it for part 2 of our Diels-Alder video. And I'll see you in the next video.